So in section 11.5, we're going to continue working with exponential functions and work towards the base of a new exponential, or base of a logarithm called the natural log. We're going to start out by reviewing compound interest. And compound interest depends on an exponential function this way right here. Here's your compound interest formula. A is your ending balance. That's how much you get after investing an amount. P, your principal, for so many years at a compounding rate of n times per year and an interest rate of r. Now the important thing about this is that you have to express r as a decimal. So for our first example, we could invest, say, $5,000. So P equals $5,000 at n is 4, meaning interest are going to be compounded 4 times a year. So 4 times a year, you're going to get interest. Our interest rate, currently interest rates are pretty low, so we'll call that 2.2%. T is going to be years. And we'll invest that, say, for 3 years. Now, the important thing about R is that it has to be written as a decimal. So 2.2% is nice, but what is 2.2% as a decimal? If I got rid of the percent sign, what would that be? What would I have to write to get it equivalently? 0.022. Yes. So 0.022. Okay. Let's plug everything in here and figure out how much we're going to get. A really stands for your amortized value. When you buy a house, you're going to get an amortization schedule. It tells you how much of that house you actually own. So it's going to be 5,000 times parentheses 1 plus 0.022 divided by 4 raised to the 4 times 3 power. Okay. Well, this is certainly not something we want to do in our heads. So take out your calculators. Let's do it that way. So kind of follow along as closely as you can. Type in the 5,000 and then a left parenthesis. Your calculator understands that there's going to be a multiplication there. You don't have to hit the times key. 1 plus 0.022, then hit the divide key. Divided by 4, right parenthesis, and then hit the exponent key. So the little up arrow here, right above the division sign. And you got your choice. You can either type in 4 times 3, which is just kind of doing it exactly, or you might look at that and go, oh, I know what 4 times 3 is. 4 times 3 is 12. And sometimes you'll find it convenient to do it that way. It just kind of depends on you. So yay, you should get 5340.1677. Let me draw your attention to one thing. We're working with money. So you should round it appropriately for money and investments. So what decimal digit should I use if I'm rounding this for money? Somebody said it. Hundredths, right? Because the smallest unit of currency we have is 1/100th of a dollar, aka a penny, 1 cent. So rounding this to the nearest penny, this should be $5,340. Point what? 17. Yeah, you want to round up in this case because this number is 5 or more, so we're going to round up when we round to the nearest hundredth. So we're looking okay on that one? Let's try another one. Actually, before I try another one, let me kind of give you a heads up here. A very easy mistake to make on these types of problems is to kind of forget to convert from 2.2% to 0.022. So what would happen if I plugged in 2.2 instead? let's see. Now keep in mind we're starting out with a modest $5,000 and we're just investing it for 3 years. Does it make sense that if I did that, I would end up with $961,502? Yeah. Well, hopefully what happens when you do that is you go, oh, wait a minute, there's something wrong, all right? I mean, I love you guys and I love teaching, but I think if I could do that, I would have retired years ago. I would have been gone, man. You'd find me on the ski slopes or someplace like that, someplace fun, but it might not be the classroom anymore. Nothing personal. Let's try another example. Like I said, hopefully, if you get an answer that just doesn't look right, fix it. So, let's try this one. Principal, this time we'll do $10,000. So quite often when you invest money in a mutual fund or something similar to that, they tell you, well, what's going to happen to a standard investment of like $10,000? Historically, the stock market receives about 11.5% interest. That figure's probably out of date. I'm sure it's within a couple percent, but I'm not sure that it's exact anymore. And let's look at investing that for T equals 7 years. And we're going to compound interest 12 times a year. So that means monthly. So every month you're going to get 1/12 of that in interest. So a little bit less than 1%. The question is how much money you're going to get when you're all said and done. Well, we're going to plug that back into this formula right here. There's one important thing I have to do before I plug that into that formula. What is it? Got to switch this to a decimal. So as a decimal, it's 0.115. Let's see about plugging everything in here. 5,000, 1 plus 0.115 over what? 12. Raised to the 12 times 7 power. Okay. So let's see how that one grinds out. 5,000. Yeah, question? Oh, yeah, no, I'm sorry. Should be 10,000. Thank you. 10,000. Thank you. 10,000 times 1 plus 0.115 divided by 12 raised to, now it depends on you. I mean, if you're good with math, maybe you'll do 12 times 7 is 84. Maybe you don't want to think that hard and you go, okay, it's just 12 times 7 power. Either way works fine. So we end up with $22,281. Rounding that to the nearest tenth, 0.4. Do I have to write the 0? Do you think on the test I'm going to want you to write the 0 or no? Yeah, you're dealing with money. I want to know what's there. I don't want to say, hey, wait a minute. Was it 38 cents and you round it up, or 42 cents and you round it down? I want to see that digit there. Yes? You want to show me what you got? Oh, okay. So the difference in yours and mine is that 12 times 7 is not in the exponent. So let's go back and re-edit that one. And what you can do to re-edit is go back here, and there's a delete key right there. Because a lot of this is good. I'll just delete that. Then we'll hit the up arrow key right here. And I dig your pink calculator. That's kind of cool. And then do 12 times 7. And now these are twins. So, thank you. No, that's certainly somebody else is going to benefit from that. All right. Are we okay with that one? Now, I've been informed that Google is really, really, I don't know, let's just say it, anal about copyright stuff. So I can't really pull up anything about, old movies and stuff like that without putting myself in trouble. So I'll just have to tell you about this one. There's an old Eddie Murphy movie called Trading Places. And in that movie, they had a standard bet. Does anyone remember what that standard bet was? It was $1. So what we're going to do is we're going to work on the next part of this stuff, which is to try and arrive at an understanding of the second most favorite constant in mathematics, which is called E. So let's take a look at what we're going to do to get E. To derive E, we're going to talk about a somewhat fictitious example. We're going to invest $1 for 1 year at an interest rate of 100%. Now keep in mind something. When we put this into our calculation, what's 100% as a decimal? 1. So basically I'm taking everything from my formula that we just dealt with for compound interest and making it a 1. And so my formula looks like this, right there. And I'm making everything a 1, which reduces it down to this right here. And we're going to see the effect of changing the amount of times that interest is compounded. How does it affect how much money you get back? So we'll start out with the most simple case, with n equal 1. So you're going to invest your dollar on January 1st. At the end of the year, you're going to get 100% interest. So if I put in a 1 here, 1 plus 1 over 1 to the 1 power, what am I going to get back? How much? Not all at once. Come on, you're supposed to make me look good. 2. You're going to get back $2, right? You get 100% interest on $1. 100% of $1 is $1. They give it to you. Add it in your account. You got $2. Let's take a look at compounding twice a year. What that would mean is that on January 1st, you invest your dollar. Halfway through the year, they give you 50% of the interest. So 50% of $1 is what? 50 cents. They add that to your account. Now you got $1.50. At the end of the year, they give you half of the interest again. What's half of $1.50? 75 cents. Add that to our account. Now we've got $2.25. So take a look at the magic that happened here. Because you're compounding more often, you get more money. Hey, that's kind of cool. This is a fun game. Let's compound quarterly. So now if you compound quarterly, that dollar turns into $2.44. So this is a fun game. Compound monthly, $2.61. And this is funny but true. 360, what does it feel like? How often are you compounding? Almost once a day. This is, in fact, daily interest, according to the banks. When they compound your interest and compound it daily, they'll use n equals 360, not n equals 365. It makes only the slightest of differences, and it probably goes back to a time when you had to do this stuff by hand, so it made the arithmetic just a little easier. But yeah, this is daily interest.
Why is it 360? Are they like trying to save money for themselves? Those 5 days?
It does save them money, but the amount is so small that you even Bill Gates would hardly notice. So what happens here is when we go from monthly up to daily interest, you made an extra dime. And if you notice, things are kind of slowing down, right? At first, we made an extra quarter, then an extra 19 cents, then 17 cents, then a dime. And now look, if we jump from daily interest to, does anyone know what this would be? Hourly. Every hour. Then that's how much you'd make. You're not even getting an extra half a penny in making that big jump. Now, if you stick with me through calculus, we can show you how to put in essentially infinity, which means that you're compounding continuously every second of every minute of every hour of the day of the year, always, nonstop, and you're going to get The second most favorite constant in mathematics, E. So, wow, what's E all about? Well, let's find E on our calculators. And you're going to find E in two places. So pull out your calculator. The first place you're going to find it is kind of near pi, which is kind of fitting because we're coming up near Pi Day. That's just 2 days away. Right above the division sign. What do I have to do to get to E here? Second, and then the divide sign should give you as many digits of E as you would ever want or need. 2.718281828, etc. Continues on and on forever without repeating. Now, the other place you can find E is right above the ln key. And in fact, that's going to be the base of the natural log. That's why we're introducing E here. So, if you hit the second key, then the ln key, it gives you E, but it's ready for some exponent. Now, you can put a 1 here and get this. But if you put a 2, you get E squared. Second, ln again, let's type in a -1. Now you get the reciprocal of E. But you should be able to get these numbers here. Okay. Now, Cole, let's kind of address one of your concerns you expressed just a minute ago. That is, looks like they're saving money. It's not going to be a lot. We're going to compare our previous example right here. Let's see what this would look like if we compounded interest continuously. And there's a formula for that. The formula for continuously compounded interest is A equals PERT. Okay. So let me remind you of some of the things in the last example. Our principal was 10 grand. The time period over which we're going to invest this was 7 years. And our interest rate was 11.5%, which of course we're going to write as a decimal. You might notice that there's one thing missing from this formula that I had in this formula, n. That's because n is kind of baked into the constant E here. So we don't have an n anymore. On the exam, I'll give you these two formulas, this one and this one. You just have to know which one to use where. But if they're not giving you an n, or if you don't have an n, then chances are you're working with continuously compounded interest.
So on the exam, are we going to receive the values like 10,000?
Oh yeah, you have to be given the values.
Are we going to be giving them just straight up, or are we going to have to take them from like a word problem?
Well, if you had to take them from a word problem, it wouldn't be like really hidden. It wouldn't be.
It takes more work.
Yeah. Well, I don't know what to tell you about that one. Yeah, you're going to have to do a modest amount of work to get it from a word problem. If you look at some of the old exams, I don't think it's really deep. So 10,000 e to the 0.115 times 7. So let's take a look at that one. See if we can't calculate that. So 10,000 second ln 0.115 times, and here you do have to hit the times key, 7. Okay. So 22,366. So are we getting a lot more money back out of this? Yeah, some. Yeah. Well, I mean, I don't know, probably like $85. So how hard do you have to work to get that $85? You get to drive to the other side of the state. You know, this is going to be a diminished return if you have to work really hard to get that extra interest. But the important thing is to see that you get this number. By the way, what would this round to? 366 point what? 0.96, yeah, 0.96. Don't round and then round it again. Don't round this. Okay, that it rounds up and then round up. You just look exactly one to the right of this number. If it's 5 or more, you round up. If it's 4 or less, you just truncate it. So about 22,366.96 dollars. How are we looking with that one? You okay with continuously compounded interest? All right. What's that? What? Oh, the double E? You mean above the comma? Oh, that's just the letter E. It has nothing to do with the number E. Yeah. And the double E here, that's for scientific notation. It stands for enter exponent. So, like 1.5 times 10 to the 6, I'd write it as 1.5 E6. So it'd be 1.5 million. So that's what that is just scientific notation. What's that? Yes? Okay. All right. Let's deal with the graph of e to the x. So there's two graphs that I have here. 2 to the x and e to the x. The question is, which one is which? So one way you could answer it is kind of by doing a little thought experiment and plotting some points. 2 to the x, e to the x. Both of these graphs are exponential functions. So that makes sense. I mean, the shape is something familiar. It gets close to the x-axis, left of the y-axis, or for negative values of x, and explodes to the right of the y-axis. So you could start out by saying, all right, well, I'll plot some values, like 0, 0, 1, or 0, 1. So that's really not a good point to distinguish between these two graphs because both graphs pass through here. In fact, one of the things you should remember from our discussion about these graphs, y equals b to the x, is that it always passes through that point. So let's give ourselves another point, like 1. 2 to the 1 is 2. E to the 1 is 2.71828, etc. And that's finally going to give us a way to distinguish between these two graphs. So that's 0, that'd be a 1 right here. And if I go all the way up here, I get a point at 1, 2. Which means this graph right here is 2 to the x. And that's going to be this top graph over here. And the other one is e to the x. But both of them are pretty similar. And you should see some familiar ideas regarding this. You've got a horizontal asymptote here at y equals 0, passing through that point and growing quickly. We're going to practice with graphing these and shifting their graphs. And how did I determine which one was which? Well, by plotting points, right? If you plug in a 1 here, if you plug in a 1 to this, let's just make a t-table for just this function, x and y, you get the point 1 and 2. And that point is only on this graph right here. So this has to be the graph of y equals 2 to the x, and the other one has to be the graph of y equals e to the x. So for e to the x, I would get the point 1, and e, or e to the first power. Well, e is about 2.718, so that's your point 1 and e right here. Again, kind of confirming that that's e to the x. Does that make sense? The thing about the graphs of the exponential functions is that I'm not really going to be that picky, and you can still graph e to the x by shifting. So let's review a couple problems for graphing here. We'll start with problem number 26. Now what I've given you on the back of this handout is the graph of y equals e to the x. Problem 26 asks us to graph y equals negative e to the x. So let me make that negative out front a little bit more clear. What's that negative going to do to our graph? Yeah, it's going to flip it around the x-axis. So instead of having a point at 0, 1, I'm going to have a point down here at 0, negative 1. And the graph's just going to point down from there. And I'm sorry if I'm making the viewer dizzy, but you're going to get something that looks like this. A mirror image just reflected down. Passing through the point 0, negative 1. Let's try problem number 28. Y equals e to the x minus 2. Hopefully you remember a little bit of our work with shifting graphs of the exponential. This one's not going to be any different. How's the minus 2 going to affect our graph? Right 2, down 2, someone's saying to the left 2, down 2. This is going to be a horizontal shift, or excuse me, a vertical shift. It's going to shift down 2. If that 2 was in the exponent, that'd be a horizontal shift. Now before I shift it down, let me remind you that this graph has an asymptote at y equals 0. That asymptote, along with the rest of this graph, has to get shifted down. So one of the things I'm going to want to see and ask to see on your graphs is the new horizontal asymptote, which is here at y equals negative 2. The other thing I'm going to want to see is how this point has been shifted. Well, just kind of like everything else, it gets shifted down by 2. So it's going to be at the point 0, negative 1. And finally, we need to kind of draw this curve. And just basically mimic what I've got there. Something that looks like that. Now if your graph accidentally touches the horizontal asymptote, no big deal. Just make sure you don't ricochet off or slice right through it, and you'll be okay. You should be able to draw a reasonable facsimile of that graph right there. One more like that one. This is my own example. It's not one from the book. Y equals e to the x plus 2 and plus 1. This time there's been 2 shifts to the graph. Give yourself a moment to see if you can figure out what each of these do. So the plus 1, how does that affect the graph? How has it been shifted? Up by 1. And the plus 2 here in the exponent. Right 2 or left 2? Which one? Left 2. Horizontal shifts are always kind of opposite of what you might think based on the sign. So it looks like it should be to the right by 2, but it's actually to the left by 2. let's start by drawing our new horizontal asymptote. The horizontal asymptote, at least the old one, was at y equals 0. Where's the new one? At y equals 1. So that's your new horizontal asymptote. Okay. Well, let's see. This point is at 0, 1. Let's see if we can't figure out where that is in our new graph. It's going to get shifted up by 1 and to the left by 2. 1, 2. What are the coordinates of my new point there? -2 and 2. Now you can sketch it in freehand from right here. There's nothing wrong with that. But I'm going to show you a little trick that you can use to earn an extra credit point here. Are we okay with how it's been shifted so far? Up by 1, to the left by 2. The other thing we can do is we can graph the y-intercept. Where does it cross the y-axis? How do you find that point? Set x equals 0. So if I set x equal to 0 to find the y-intercept, I'll get y equals e to the 0 plus 2. So e to the 0 plus 2 plus 1, which is going to be e squared plus 1. And you're probably going to need to take out your calculator for that. It's going to be about 7.39, I'm guessing. How about 8 point, plus 1, 8.39, roughly speaking. So with a little bit of help, it'll just barely fit on our graph. So 8 and a little bit higher. That's that point. And if you want to graph that one accurately on an exam, you'll probably get some extra credit. So we'll play connect the dots. And get something like this. Okay, so that's the graph of your exponential function there. Now what I'm going to do is I'm going to stop the video here. We do have a little bit left to cover, but I'm not going to put it as part of this video. Maybe make another video, and I'll send you the link. Oh no.
Did you record?
I think I did. Yeah. Whew. Yeah, let's hold our breath, and it looks like I did record.